Before we start to look at deep learning methods for numerically encoding small molecules, we will quickly look at some alternatives for generating numerical representations that do not require deep learning methods. The reason for that is, if we make the effort to train large computationally expensive deep learning models, we want to make sure that the resulting numerical representations lead to better prediction results than more traditional methods that might be easier to determine. The reason why we want to have numerical representations for small molecules is the same reason why we generated numerical protein representations. When we want to make predictions for small molecules, we need a numerical representation of the small molecule that contains as much meaningful information about the small molecule as possible. We can then use this numerical representation as the input for a machine learning model, which we can train to predict a property of interest. One way of numerically encoding small molecules is to simply compute certain molecular features and store these in a numerical vector. Typically, those numerical representations are referred to as molecular descriptors, and they can contain information such as the molecular weight, number of atoms, number of bonds and rings in the molecule. These features can be easily computed. But also more complex descriptors are typically included, such as information about the hydrophobicity of a molecule, which describes how much a molecule is attracted to or repelled from water. Another example would be geometric descriptors that describe the geometric shape of the molecule. All of these features would then be stored in a single vector, and this vector can then be used as a numerical small molecule representation. A wide variety of different molecular descriptors can be calculated in Python using RDKit, which is an open source cheminformatics software library designed for working with molecular structures and performing tasks such as molecular descriptor calculations. The RDKit package has a built-in module named descriptors that stores over 200 different functions for calculating different molecular descriptors. An alternative to molecular descriptors are molecular fingerprints, which are typically binary vectors containing as entries only zeros and ones, where each entry typically encodes if a certain chemical property is present in the molecule. We are now going to shortly look at 3 examples of such molecular fingerprints. 2 of these are based on representing the molecule as a graph with nodes and edges. Those are the Morgan fingerprints and the RDKit fingerprints, and we will have a closer look at those fingerprints on the next slide. Another example are the max keys that are somewhat similar to the molecular descriptors we have seen on the previous slide. In max keys, each entry contains the information if a certain chemical structure is present in a molecule. Basically, we can see every entry as a question regarding the properties of a molecule, where the answer to each question is either yes or no. For example, a question could be whether the molecule contains a ring of size 4, or another question could be, are there fewer than 3 oxygen atoms present in the molecule? Max keys are typically 166-dimensional binary fingerprints, which means they provide yes and no answers to 166 questions regarding the molecule. As for the molecular descriptors, the most common molecular fingerprints can be calculated using the Python package RDKit. For example, you can encode the small molecule for which you want to compute fingerprint through Smiles representations that we have seen in the previous video, and we can use this Smiles representation as the input for the RDKit functions. One example of graph-based molecular fingerprints are the so-called Morgan fingerprints. Here we are looking at a specific implementation of Morgan fingerprints, the ECFPs, which is short for Extended Connectivity Fingerprints. To calculate ECFPs, molecules are represented as graphs by interpreting the atoms of the molecule as nodes of the graph and the chemical bonds of the molecule as edges of the graph. Then we calculate for each bond and each atom a feature vector storing information about the atom and bond type. For example, for each bond, we save the information what type of bond we have, and for every atom, we calculate information such as the atom type, its mass, charge, and so on. Afterwards, these vectors are updated by iteratively applying expert-defined functions to summarize aspects of neighboring atoms and bonds. So, for example, to update atom 1, in this image, we would use information about the atoms 6, 7, and 2, and also about the bond types with which they are connected to atom 1. This results in a better vector representation for atom 1 that now not only contains information about the atom itself, but also about the neighboring bonds and atoms. Since all atoms and bonds are updated simultaneously, this is also true for neighboring atoms and bonds. And if we now update an atom or bond vector again, we also get information about the atoms and bonds that are 2 steps away, and we not only get information about the direct neighbors. This is true because if we imagine that we now update vector 1 again, we would, for example, use information about atom number 2. But since atom number 2 has been also updated, it already stores also information about atom 3 and 9. Hence, if we update atom 1 by using information from atom 2, we can also get information about atom 3 and 9. This updating process is done for all atoms, and the procedure is repeated for a predefined number of steps, typically 2 or 3 times. After the iteration process, all atom and bond feature vectors from all iterations are used as the input of a hash function to produce a single binary vector with structural information about the molecule. Usually, this vector has 1024 entries. Finally, we're going to look at how to generate RD-kit fingerprints. Similar as for the Morgan fingerprint, we are interpreting the molecule as a graph. Then we identify all subgraphs of this entire graph that do not exceed a certain size. For example, all subgraphs that do not contain more than 7 bonds. And finally, we encode in a binary vector what kind of subgraphs are present in our molecule.